Welcome back, students. In the previous video, we had seen the introductory concepts of Lagrange's mean value theorem and discussed the statement of Lagrange's mean value theorem. In today's video, we shall see a couple of problems related to verification of Lagrange's mean value theorem. So let us start today's video. Now, before moving on to the problems, let us have a brief recap of what does the statement of Lagrange's mean value theorem say. See, it says that if there is a function from AB to R, closed interval AB to R, that means the input of the function will be taken from the closed interval AB and the output of the function will be any real number. If that is a function such that the function is continuous in closed interval AB and the function is differentiable in open interval AB. Now these are the two conditions, hypothesis of this Lagrange's mean value theorem. If these two conditions hold, then we can conclude that there exists a point in between A and B such that derivative of the function at that point is equal to the difference of the functional values at the boundary points divided by the difference of the boundary points. That is, f dash c is equal to fb minus fa by b minus a. It means you can find a point C such that this equation will hold true. Now see, if you have to verify Lagrange's mean value theorem, what you have to do? A function will be given. This function f will be explicitly given to you and the boundary points A and B will also be given to you. You have to verify, means you have to first see whether the function satisfies these two conditions or not. The function is continuous in AB and differentiable in AB or not. If these two conditions hold, you will have to find a point C such that this equation holds. This is the process of verification of Lagrange's mean value theorem. So let us see the first example of how to verify a Lagrange's mean value theorem. This is our first problem. It says that you have to verify LMVT, that is Lagrange's mean value theorem, for the function fx equal to x square plus 3x plus 2 in the interval 1, 2. Now, how to start this problem? I told you before also, first you have to verify that these two conditions hold true or not. If initially these two conditions do not hold true, then the problem ends over there. So let us first verify if the function is continuous and differentiable in AB or not. See, what type of function is this? This is a simple algebraic function, okay, x square plus 3x plus 2. Now to verify whether it is continuous or not, the simplest way is that you have to find out if there are any points in between the interval, including the boundary points, which when replaced in place of x makes the function undefined or not, or makes the function tend towards plus infinity or minus infinity or not. See, since this is an algebraic function, a polynomial type of function, whatever value of x you put in place over here, the function will never become undefined. See, between 1 and 2, including 1 and 2, whatever value you put in place of x, you will get a finite number. You will never get the function to become undefined. So you can safely tell that here fx being a polynomial function, it is continuous in 1, 2. Why did we write this function to be continuous? I hope it is clear to you. Since it is a polynomial function, whatever value of x you extract in between 1 and 2, including 1 and 2, the function will give a finite value. It will not become undefined. Okay, that's why the function, you can safely tell the function is continuous in 1 and 2. Now see, the first part is done. Now for the next part, whether the function is differentiable in AB or not, you have to find out the derivative. Now see, f dash x equal to 2x plus 3, simple differentiation over here. Now this 2x plus 3 is also a polynomial function, simple polynomial function. See, whatever value of x you put in between 1 and 2, take from 1 and 2, you will get a finite value. So here also you can tell, also here f dash x is defined in 1, 2, or in other words you can tell f dash x or exist in AB. That means f is differentiable in AB. Here AB is 1 and 2. So the simplest part is that you have to check whether there are any undefined points or not for the function. See, I'll give you an example. If the function would have been like this, fx equal to 1 by x, okay, and you have to find out between plus 1 and minus 1, minus 1 and plus 1, sorry, minus 1 and plus 1. Suppose the interval is minus 1 plus 1 and the function is 1 by x. So there exists a point 0. If you put in place of x, the function becomes undefined. So 0 is a point of discontinuity over here, and 0 lies between minus 1 and plus 1. So over here, you cannot tell the function is continuous in minus 1 and plus 1. But over here, since there are no undefined points between the interval, so you can tell the function is continuous. Same logic follows for the derivative also. You find out the derivative, see what the derivative becomes, then you check whether there are any undefined points for the derivative in the interval or not. Since it is a polynomial function, simple polynomial function, there are no undefined points, so you can safely tell that the functional derivative exists in between 1 and 2. So both the points hold true for this problem. The function is continuous and the derivative exists. Now see, then you will have to find out a point C in between 1 and 2 such that this equation holds true. Now what is this equation? See, now here fb minus fa by b minus a equal to, here b is the right hand boundary, that is f2, minus fa, that is f1, by b minus a, that is 2 minus 1 means 1, which is equal to, see what is f2, put 2 in place of x, f of 2 means 2 in place of x, that is 4 plus 3 into 2, 6 plus 2 minus f of 1, 1 plus 3 plus 2 divided by 2 minus 1 means 1, which is equal to 4 plus 6 plus 2. So this 2 and this 2 gets cancelled, 3 plus 1 4 and this 4 gets cancelled, 6 by 1, that is equal to 6. So over here fb minus fa by b minus a is equal to 6. So you will have to find out a point C in between 1 and 2 such that derivative of the function at that point is equal to 6. If LMVT holds true, then we can, I don't know if we can, but let us assume we can, okay, then we can, or it's better to write we may, find a point C C in between 1 and 2 such that f dash C equal to fb minus fa by b minus a, that is 6. Now what is f dash C? See, the derivative f dash x equal to 2x plus 3. So f dash C equal to 2c plus 3, that is equal to 6. I hope everyone understood how did we get 2c plus 3. Since f dash x equal to 2x plus 3, put c in place of x, 2c plus 3 is equal to 6, which implies if you do a simple calculation, you can find c equal to 3 will go this side, 6 minus 3 is 3, and 2 goes this side, that is 3 by 2, which is 1.5. So you can find a point C, that is 1.5, such that f dash of 1.5 equal to fb minus fa by b minus a. Now the point of concern is that whether this point lies between 1 and 2 or not. 1.5 obviously lies between 1 and 2. So over here, logically, we found a point between 1 and 2 which satisfies this equation. This is the verification. Verification is nothing but you have to find out a point C. Anyhow, you have to find out a point C which satisfies this equation. We found a point C that lies between 1 and 2 which satisfies this equation. Okay? So you have to write C equal to this. So we found a point C equal to 1.5 which belongs to 1 and 2 such that f dash C equal to fb minus fa by b minus a. Finally, you have to write hence Lagrange's mean value theorem is verified. Okay? So this is the process of verification of Lagrange's mean value theorem. You have to first check whether these two conditions hold true or not. If these two conditions do not hold true, the problem ends over there. If these two conditions hold true, then you have to proceed to the next level. That is, you have to find out a point C which lies between the interval a, b over here 1 and 2 such that this equation holds true. Let us move on to the next example. Okay, so this is our next problem. It says that verify Lagrange's mean value theorem for the function fx equal to cos x in between the interval 0 and pi by 2. Now see, we all know that trigonometric functions like sin x, cos x, these are all continuous functions. There are no points of discontinuity in it. But for the sake of understanding of this problem, let us see what the diagrammatic representation of fx equal to cos x is in between 0 and pi by 2. If this is 0, this is pi by 2 and this is pi, we all know that cos x goes like this. The point at which cos x cuts the x-axis, this is the x-axis, is pi by 2. Then this extreme dip is pi, and at 0 it is 1. So value of cos at 0 is 1, value of cos at pi by 2 is 0. But nowhere, see, our point of concern is only between 0 and pi by 2, that is only between this 0 and pi by 2. So only at this sector, whatever happens afterwards, it's not our lookout. However, in between 0 and pi by 2, we can see that the function is continuous. There are no points of break or discontinuity. Neither the function tends to infinite anywhere between 0 and pi by 2. So we can safely tell that this function is continuous in between 0 and pi by 2. Here fx equal to cos x is continuous in 0 and pi by 2. That is the first part, that is done. Now for the next part, whether f is differentiable in between the open interval ab, that is 0 and pi by 2 or not, we have to differentiate the function. What is the differentiation of fx? If fx equal to cos x, then f dash x equal to minus sin x. For the time being, forget about the minus. See, if sin x is continuous, then minus of sin x is also continuous. For sin x also, we know the function is always continuous. There are no points of discontinuity of sin x anywhere in the x-axis. Okay, so here also, see, for the, if I draw the diagram of sin x is like this. If this is 0, at this point, extreme peak, that is pi by 2. So between 0 and pi by 2, see, sin x, there is no point of discontinuity. So if sin x is continuous, then minus of sin x is also continuous in between 0 and pi by 2. So we can safely tell that f dash x equal to minus sin x is also defined in 0 and pi by 2. If a function is always continuous, there are no points of discontinuity, jump discontinuity in it. So the function is also defined. We can tell the function is also defined. So here, see, f is continuous in NB and the derivative also exists in the open interval AB, that is 0 and pi by 2. So the first two conditions of Lagrange's mean value theorem are satisfied, holds true. Now our point is to find out now a point C in between 0 and pi by 2 which satisfies this equation. So let us assume that there exists a point C in between 0 and pi by 2 such that f dash C equal to fb, that is f of pi by 2 minus fa, that is f of 0 by b minus a, that is pi by 2 minus 0. Now what is f dash c, or f dash c means minus of sin c, f dash x equal to minus of sin x, that is f dash c equal to minus of sin c, f of pi by 2. So cos pi by 2, we all know cos pi by 2 is 0. F of 0, that is cos 0. Cos 0 is 1 by pi by 2 minus 0, that is pi by 2, which is equal to minus 2 by pi. So minus of sin c equal to minus 2 by pi, or sin c equal to 2 by pi, which implies, or c equal to sin inverse 2 by pi. You have the liberty of using your calculator, scientific calculator. You can use the scientific calculator, check out the value of sin inverse 2 by pi. You can easily find out whatever value you get, that obviously lies between 0 and pi by 2. So here it shows that you can over here find a point C which lies between AB over here 0 and pi by 2 such that this equation holds true. Here also we can safely tell that yes, the Lagrange's theorem has been verified. So my dear students, these are the two examples of verification of Lagrange's mean value theorem that we had seen in today's video. If you have liked today's video, understood today's problem, then do like my page, subscribe to my channel and share it with your friends. Till then, goodbye.